all button. So right now your antenna is like this, and if you want to pan this section, you can drag and from here. If you want to rotate and see different faces, you can do that manually. So this is a very basic antenna that we have yesterday designed, and here what we did, we designed a coaxial cable, and at the one end of the coaxial cable we added the wave port, and other end of the coaxial cable is touching the ground plane and the patch, and we have drilled this hole here. So let us explore it further. So first, let me make everything invisible. Okay. So now there is nothing present there. Now, one by one, I am going to uh, view this. So first, let us see what is the ground plane is looking like. So we select the ground and make it visible from this show selected object in active view. Okay. Now when we have selected any object, then its color will be like this. Otherwise the default color that we have set, that will be there. So in ground view you can see that this is a simple rectangle cuboid, and we have a hole at this position. And now if we see the uh, outer conductor of the coaxial cable, that is there. So if I make it visible, again click anywhere, so you can see that this coaxial, the outer conductor of the coaxial cable is touching the ground. Okay, and it is hollow. Now let us view the substrate of coaxial cable, make it visible, and click here. So now you can see this one is also visible. Okay, so now it appears that it is not hollow, but let us view the top view. When you go to the top view, you can see that we can zoom in. So here we have a hollow part. Okay, now let us make the center pin visible. So this is the center pin, and I have made it visible. Now it is visible, and again go to the isometric view. So you see in the ground plane, our substrate of the coaxial cable is touching the ground, uh, and the outer conductor of the coaxial cable is also touching the ground. Their height is same as the ground. Then the center pin of the coaxial cable is extended above the ground, and how much it is extended. So let us fit all, and let me rotate it like this. Okay. Now I will make the substrate visible. So once we made the substrate visible, you can see that this coaxial cable, the center pin of the coaxial cable, is extending till the height of the substrate. Okay. Now we again create view the patch and patch, then make it visible. So now we have a whole antenna, and you see this small circle that is representing that the coaxial cable, the center pin of the coaxial cable is at this point, is reaching up to this point. So therefore it is displaying the circle here. Okay. Now uh, in 3D modeling, in HFSS, if we have multiple objects, and those objects are very different at different positions. So let me create another file. So click on desktop. From here you can insert a HFSS project, and let me draw something. So this is an object, and we are making it right now. It is a vacuum, so we change that it to Teflon and change the color. Okay. Now let us create another egg box. Okay, and this box is made up of copper. The color is yellow, and click OK. Okay. So now you see there are two objects, and if we see it by all the angles, these objects are completely isolated. So when these objects are not touching each other or they are not intersecting, then there is no problem. But what happens if the objects are intersecting with each other? So for that, I am selecting this green Teflon box and going to its property. Now either I double click or I can set from properties. So here we can see that if we extend the length of the y, then it might intersect with this. So let me extend this length, and right now it is minus 1.2. The length is cannot be negative, but it is a relative length. So it is relative to this position. So from minus 1 it is starting and it is extending up to minus 1.2. That is minus 1 plus minus 1.2, that is minus 2.2. So this end is minus 1, this end is 2 minus 2.2. So let us make it 5 mm. So now it will extend from 0 to minus 1 to 4, and very big. Let us make it 1.5. Okay. So I guess this is intersecting now. Um, okay, it is just touching. So if we go to simulation and click on validation, then right now when I click on the validation, it is displaying the 3D model is okay. Okay. So let me add something more in this. Let's go to the top view, and in the x-axis if we increase the box, then it might result some into something. So let me give it 2. Okay, I hope now we have some interact. Okay, so now you can see that both these boxes, they are intersecting, they have some common portion. So if I click on the validation now, now you can see that the 3D model, it is also giving some error. Okay, so what is that error? Let's clear the previous message and then run it again. So it says box 2 and box 1, that are the name of the boxes that we have just created, and in these boxes they are intersecting. So we cannot have multiple objects intersect in HFS. Okay, if they are of different shapes, they cannot. Uh, Sorry, if they are made up of different materials, they cannot intersect. So what we can do, we need to apply some options. We need to apply some Boolean options, and one special case I am going to show you, that is, let me give it extend from minus 2, minus 2, minus 2, and 4 4 mm, 4 mm, and 4 mm. So I have recreated this cube as like this, and I'm creating it minus 1, minus 1, minus 1, and put size I'm giving 2, 2, and 2. So the first cube is of 4 by 4 by 4, and second cube is 3 by 3 by 3. Okay. Now when we click here, we see only the outer cube. So what we can do, we can select this cube and make it transparent, uh, and click OK. So now when you click here, you see that both cubes are visible, and we see that the smaller cube is completely embedded inside this cube. Okay, so now if I click here and clear the warning message and start validation, now there is no error, that is the 3D model is okay. But if we remove this cube like this, I make it -3. So now it is partially intersecting. It is not completely absorbed. So at this position, when we click here, we are getting an error. So the conclusion is, whenever we are modeling, if the objects are completely separate, then there is no problem. If the objects are completely merged inside, a small object is completely merged inside the bigger object, then there is no issue. But if any object is having two mediums, for example, this yellow cube, at this position, you can see that the outer is made up of air or space, and in this position, then it has a different medium. So a single object cannot extend in two mediums. Okay, so that is why we need to do some uh, processing, and for that we go to draw, and now let us explore what we can do with this. So you can see that right now we were using 3D geometry. We used cube and cylinder, and this one is also a cylinder, but it is a polyhedron. We will explore it in just a few minutes. And these are the 2D surfaces. We can draw 2D surfaces in here, and these are the linear surfaces. Okay. Then this is a special box that we will discuss here. Now you see these objects, they are disabled right now. These operations, they are disabled. So if I select one object, then you can see that these o- these six operations, they have become active, and this one is also active. So let us explore what is this. This operation, this is called the first move operation. So once it is not like that once we have created something, we cannot shift its position. If you want to shift the position of any object, we can select that object and select this operation. It is called move, and we sell it consider relative positioning. So consider this is my point 1 and this is my point 2. Okay, so this will act as a reference, and on the left side you can see that it is displaying position 1 and position 2, reference position and current position. So from these points it is calculating a vector, and uh, that vector uh, that vector displacement will be added here. Okay, so that now the cube has been taken out. So, now if you want, we did it manually. Now you want to increase the accuracy of that. So what you can do, you can go to the cube, and you see earlier there was only one option there. Now it has the operation that we performed on this cube, that is also there. So if we double click here, we can see that move vector. That is the the, the difference of the 2 points that we have taken. That is known as move vector, and we can change this move vector. We can make it variable. So let me make it as x position, and I will give it 1 mm length. Okay, and now click OK. So now you Okay, so now you can see that that object has moved, but it has not cleared the boundary. Now the variable is here. We can change this variable to 2, and it is shifting like this. 3, 4. Okay, so this is happening because earlier we were giving direction in negative x direction, and now we are moving in positive x direction. So at this point, this cube is like this. Okay, and let us see the it. Let us see the isometric view. So this is our current object. Now, if we want to simulate this, we will be getting an error because this yellow cube is partially inside the green cube. So that is not permitted. What we can do here, we can go to draw and select both of these cubes. Okay. Now, when we selected both of these cubes, you see these buttons are also active. Okay. So if I selected only one object, then these operations are possible. So we have already explored this move position. Now let us explore the rotate position. Okay. So when I click rotate, it is asking me to rotate in along the axis. We can either rotate this cube in x-axis, y-axis, or z-axis. Then let me give it 45-degree ready, and you can select the unit. So by default it is set to degree. I am giving it a 45-degree rotation along the z axis. Okay, so click ok. Now let me make this cube invisible right now, and we are rotating in the z axis. Click on the isometric view and set on now. So initially, the order of operations, you see, initially we applied the operation of movement, then we applied the rotation. Okay, both these operations are attached to this object, and you can change that later on. Okay, so if I want to make it a variable, then I can give it at like a 30-degree. Okay, so this uh, what we say, can you identify that? Is it this cube really rotated in this z-axis only? If I go to the top view, you see we have given a 30-degree. Now, if we give 45-degree, this cube is looking like this. Okay. Now click on 90-degree, 135. So like this, it is moving inside. Now, what is the significance of this? So if you see, uh, we are rotating along the z axis. Okay, so that cube was present earlier at this position. If I give the rotation 0, this is the current position. Now the other variable was x position. Let me give it as 0. So the position is like this, and let me give it 3. 3 is too much. 2. Okay, so now this cube is centered around the z-axis. Now if I give it a rotation 45-degree, it is rotating like this. 90-degree, we will not observe anything, but it is rotating 90-degree. So the position, how much it is far away from the z-axis, that defines its rotation. Okay, so whenever we are rotating, that rotation is done at this position only. Okay, now let me select it once again, and now the third option is mirror option. Okay, so when I click on the mirror, then asks us to select a plane or a normal variable. So I'm clicking like this. Okay, now it has made If I uh, we can delete any operation by selecting it and click on the delete button. Okay, so this is now giving a 60-degree rotation. And now if I select this object and again create a mirror, then you can see this face of this object. It is making the normal of this will make an angle of 120 degree. Initially it was 60 degree. So we are making a mirror along this plane, y and z plane. Okay, so let us explore what are the options we have. So the base position, it asks us to give a base position from which we are going to rotate, and then it is asking a normal position. The normal position is a normal position is for a surface. So we are giving in x-axis we are giving a -1. That means we are mirror our mirror is placed in the yz plane, and we are considering the base position is 2.8 in x-axis. So what happens if I select a different base position? So I just control Z and select the object. Now again click on this mirror, and from this position I am taking a mirror. So now my mirror will be placed at this point in YZ plane. Okay, like this. So it has created a copy with respect to that particular point. Okay, so I think you understood how to use these operations. Now again select this, and these three operations that are duplicate along a line. So duplicating an object means we are again moving, but this time in addition to movement, we are okay. So when we click on the duplicate along the line, then it will perform the same operation as movement, but this time we are able to create an another copy. Earlier we were just making or doing all the operations at the position, the original object, but now we can create a copy of that. So uh, currently, if it says here we have an argument that is called total number. So after performing this operation, how many total number of objects of this object should have? So it should have two objects. And if I click OK and now select fit all, so you can see both these. This is the box one, the original box. This is the copy, and this is the last operation. So these three operations should have been copied here. So let us check. So this is the box which has all these operations. Okay, so sometimes we want the duplicate copy to have a separate object name, and sometimes we want that object to have to not create another object. Okay, so in that case, what we can do, we can select this again, or let me delete this one and select this object. Click OK, and now we have two copies. But okay, sorry. Now we have two. We'll be having two copies again, but this time I am selecting this checkbox that says attached to original object. If we click here, then click OK. So now both there are two cubes, but both of them are in the same object. Okay, so this is how you can create multiple copies of an object, and you can either attach them to the original or you can have separate copies. Okay, similarly this was the result of a duplicate along a line, that is similar to move object. We can also make a copy of these objects by rotating them. So let us make a copy of this, and uh, here the number of objects are n. Okay, 2, and I am creating a duplicate copy at 90 degree. Let us create, and now if I click fit all, so we can see that these objects made a copy in 90-degree rotation along the z-axis. Okay, we can create mirror, uh, and this was not attached, so let me select this one, duplicate along the mirror. Okay, now we have three objects, box 2, box 2 underscore 1, that means it is an extended version of this, and this one is extended version of this. Okay, now all these objects, now we have selected two objects, then you are able to see that we have some extra operations that are available. The first operation is unite. Unite represents addition of these objects. So first we select all these three objects and click on unite. So now all these objects are part of this. Okay, and you can see here these are the subparts. If I click on any operation here and press delete, so if I click at this mirror image and delete the operation, then the result of that was this box, so that will be deleted. Okay, and now the whole object are deleted. Okay, that not a single one. So let us control z, and this is the object we currently have. Go to the isometric view, and now let us make this bigger visible. Okay, so now you see that we have multiple objects, but this object and this cube. So this cube is intersecting with this. So what we it will not allow us to uh, simulate. So in order to simulate, what we need to do, we need to select both the objects, go to draw, and now in boolean operations, these are the boolean operations. What we can do, we can either have an intersection of both the objects. So if we have the intersection, then this will be the resultant object, or we can select both the objects and select subtract. Now in this subtract operation, the blank part and tool part are very important. Blank part is the original part from which you want to subtract, and these are the tool parts that you want to subtract. Then uh, if we want to keep that part, then we make a clone of that. Otherwise we can just temporarily create an object to subtract and subtract it. Okay, so I'm keeping both. Now we have, let us clear. Now let us check in the simulation, this validation. Now you see this 3D model is complete. Okay, there are no errors regarding the 3D model. So by using this, we can create any geometry, and it all depend on your creativity, how you handle and how you can imagine your structure. Okay. Okay, so this was the basic Boolean operations. Now we will go back to our. We have already done this Boolean operations when we were designing the coaxial cable. Okay, so yesterday we were getting some errors when we were trying to simulate. So this was the concept behind that, in which we have to make sure that all the objects are in a single medium only. Okay, their surroundings can change, but their their whole dimension should be in a single medium. Okay, now uh, yesterday we have created a coaxial feeding microstrip patch antenna, and uh, I also give you we also use the model network, and we use the waveport. So in waveport, I told you that we can have in the excitation. If we go to excitation, select it and go to post processing. In post processing, there is an option that is called de-embedding. So what is de-embedding basically? So in the back side, you can see. Let me click. This option is fit selected. So if you want to focus on one particular object, you can select that object and select fit here. Okay. So now let me go to excitation again. So right now you will be okay. Let me make it clear by height. I'm making all objects invisible, and I'm creating making only this object is visible. Okay. Now when I select this, you see this face has been selected, and it is displaying that a waveport is there, and it is giving exciting the signal in this direction. Now double click here and go to post processing, select de-embedding. Now I'll de-embed. It is currently 0. Let me give it 10 mm. Okay, let me cancel it, and here in design, in the properties, we have this variable L embed. We make it 10, and again select this. So now this face, the face at which we applied the wave code, that will be moved with this variable. Okay, so that is called post processing, and why it is important, you will see in just a few minutes. Okay, so this waveport de-embedding means earlier the waveport was attached here, our signal was connected here, and this part is acting as a transmission line. So when our signal is passing through this and at this position, our antenna is connected, right? So whenever we are calculating the parameters of this antenna, we are calculating the S parameter, we are calculating the Z parameters. So the Z parameters, from the theory of transmission line, we know that when we move along the transmission line, the VSWR remains constant, but the impedance varies. So the Z parameter will vary according to this length. Okay. So if we are connecting the if we are connecting this antenna, uh, if we are connecting our device in the VNA, then the length of the transmission line that we are using, that will affect our results. So in order to identify that our results do not get affected, what we need to do, we need to match the antenna terminal to 50 ohm, because most of the coaxial lines they are of 50 ohm. That has a reason that in coaxial lines, if we want low noises, then we need to give it around 27 ohm impedance, and if we want high power, then we need to apply a 75 ohm. So the geometric mean of these two is around 49 something. Then the researchers have selected a 50 ohm as a base impedance for coaxial lines, and so all the coaxial lines that we are going to use during our research, that will be of 50 ohm. So it is necessary that whatever microwave device you are designing, whether it is a transmission line, a filter, or an antenna, or any other equipment, must match with a 50 ohm transmission line. So when the antenna terminal is matched with the 50 ohm, then the length of the transmission line from your device to test device does not affect the results much. Okay, so let me show you this one. So here I have created another antenna, and it is also a simple microstrip patch antenna. And what you we can now let us explore this antenna. So from the model, what we see, we have three different materials here. we have an air that is for the region. Okay, so this we have to add in all the designs. Then we have a ground plane. Okay, this is the ground plane, and you can see this ground plane. These are the positions, and these are the values for this. So it is the width of the ground plane is 50 mm, 50 by 50. It is a square uh, uh, shape, square in shape. And after ground we have a substrate that is also of the same length, 50 by 50. Now you see in z axis it is starting from t, whereas the ground plane was starting from 0, and the height of the ground plane was t. So we are stacking it. Then the height of the substrate is 1.5 to 4 mm. So because we all the dimensions, all the materials that are made in US, they follow the mils. They do not follow the millimeter measurement. They follow the mil measurement. So it is a 10 mil dimension, I think. Okay. Then we have a patch. So in patch, you can see we have just created a box. The dimension of this patch is 38 in width and 28 in length. Okay, and we have positioned it to make it symmetric. We started this patch from -19. Then we have designed if let me delete these operations. Okay, so whenever we have some objects attached to any object and we delete the operation, so they will though the objects that were attached or cut, they will be they will be created, but their material will not be assigned there because they are not taking the property of material. Okay, so I now you see I have a feed line that is starting from this position and it is touching the patch. This is my patch and this is my feed line. And the feed line, it is a WC, and for FR I am using the substrate as FR4. For that the width of the microstrip line for 50 ohm, that comes out to be 2.9 mm. Okay, and length we can extend up to whatever points we want. Then uh, we have two cuts placed on this. So these cuts represent the insect feeding. So our overall structure will be like we add this patch with the feed, uh, create a union unit operation. So right now our patch is like this. Now we cut these two, we subtract these two, and we don't want to keep them, so we did not selected the clone copy operation. Now you see this is the own microstrip patch antenna, and the feed line, the resultant feed line that is starting from here, and it is inserting in the patch. So this kind of feeding is called insert feeding, in which the feed terminal is inserted inside the patch. Okay, so by the controlling this feeding, this depth in length, we can control the impedance matching. So this has this cut was minus W cut, that was the width of this cut, and L in is length of the insect. Okay, so from here we can see this L in. If I make it point 1. Okay, why I did not make it 0. Let us click 0 and enter. So here you see there is an error. Body could not be created because I created a 3 object, but I gave one of the dimension as 0. So that gives me an error. So what I can do, I can give it, if I want to completely eliminate, what I can give 0.001. So it has no impact here. but it is still present there, but it is not there. And if I give it 5, similarly the width of the cut we can control. So why we are parameterizing these, so that we can check all the possibilities. Okay. So whenever you are designing, you must consider that we give this all the dimensions a variable value. Okay. Let me reset it to 1 and the 7. Okay. Now it has one more object, that is sheet. These are the solid objects, that means 3D objects. Now we have some planar objects that are like this. It is a sheet. So if I click here, rectangle one, this one is a sheet. Okay. So I'm showing you a typical geometry of a microstrip line. So in microstrip line, we have a ground plane. Then on that ground plane, we have some substrates, and the substrate height is typically higher. Then, okay, sorry, this is a typical PCB sheet in which the cross-section view of a PCB, in which we have a ground a copper layer, then a substrate, and again a copper layer. So when we are designing, we are basically etching some part of this upper layer so that to design our antenna, and sometimes we also etch on the ground layers also. So in a typical microstrip line, the cross-section view of that looks something like this. Okay, I'm just increasing the height of the uh, ground so that it can be clearly visible. So this is the cross-section view of a typical microstrip line, and here you see this ground is very wide, and this is the width of our transmission line to which the center connector of the coaxial cable will be connected. So this width this width controls the how much the characteristic impedance of this microstrip line will have. Okay. So we are for our purpose we are selecting this substrate as FR4 for thickness of 1.5 to 4 mm. So this thickness comes out to be 2.9 mm. Okay. So now, in order to add excite this antenna, what we can do, we can have two type of ports. And first, I am telling you about the wave port. So wave port, in wave port, okay. So you see this blank. This reason, this will be a complete sheet. I am not filling it so that you can make a relative understanding. So this microstrip line, this way, sheet should start from the ground, and it should extend up to certain point here, and in this direction, in this direction also. Okay. So the amount by which it should uh, extend, that depends on the height of the substrate and this width. So typically it is h plus 3 times the width. So from this point to this point, this length would be 3 times the width. This length will also be the 3 times the width, and this height, it will be 6 times the height of this substrate. Okay, so this we keep in mind, so that when we are exciting the waveport, it is exciting only in a proper mode. And sometimes if you don't have sufficient uh, space available, like you are designing a MIMO antenna in which more than one transmission lines are there, and you have to design the phases, then what you can do, either you can make it small, but there is a limit beyond which it will give some unexpected results. So what you can do, you can make a sheet like this, and I am like this. So you see this new sheet, it is touching both the ground and the microstrip line. Okay, and you can give here as a lump port, but lump port is different from wave port. Lump port does not allow you de-embedding, and there are other ports that we will explore later. But right now there are two ports that we have discussed: wave port and lump port. Wave port is gives us more accurate result, and it gives us more flexibility. And lump port, it will require very small area to simulate here. Okay, so I am assigning it a wave port here. Now let me validate. So the remaining settings, okay, so once we have created a sheet, what yesterday we have selected a face, and this time let me delete this. Okay, go to this design, and in excited, this is our and uh, feeding. And if we rotate, we see that the direction of the incoming signal will be like this. Okay. So let me delete this feed, and now I select this, go to the front view. So whenever you are assigning a wave port, you have to assign the line, feeding line. So select this, and click on the assign excitation. In assign excitation, select a port and wave port. Now you have to give an integration line. So click on new line. Is the starting position of this new line will be the ground plane, and ending position will be the micro strip line. Okay, you don't have to extend this up to this point. Click next, and finish. Then okay, so now we have created a waveport. We can, you can name this waveport to your understanding. Currently we are selecting only this one. Select the post processing and select the de-embedding selected. Make it LDEM. That is the variable that we have earlier created, and this variable we are creating in a post processing step. Okay, now uh, yesterday we have selected the region, so here this region we have selected, and as we have put this wave port in the minus y direction. So if we go through here, we see in minus y direction we are not at padding. In all the directions we are padding with 20 mm. uh, we should have added it to 50 mm, but for our example we are just considering. For demonstration I am using this, but it should be at least lambda by 4 according to your frequency of use. Okay, so now go to simulation and click validate. You see all the operations are okay. 3D model is okay, design settings are okay, boundary conditions are okay, mesh operations are okay, analysis setup, it is explore this. Analysis setup we are selecting at 5 gigahertz, and the sweep is from 2 to 3 gigahertz. So let me reset this analysis setup, it is 2.5 gigahertz. Now validation is okay. Now I select this analysis and right click here and click on analyze. So the analysis is started. Okay, so analysis is completed. Let us check the results. The result are like this. From here we select the model solution report rectangular plot as parameters. Click on and it will display a new result. Okay, so currently it is operating at 2.4 gigahertz. And okay, if we see the z parameters, the peak of the real part is slightly less than at this point, but we see the dip in the S11 is more than 2.44 gigahertz. So the reason is S1 this S11 is representing the impedance matching. It is not representing the overall resonance. But with this parameter, we are able to identify the resonance. Resonance is the point where your real impedance is maximum and your imaginary impedance is zero. Okay, so around this point we have a resonance. Okay, now if we go here and select top value, fit all, and now I am going to make some changes. I am going to change the L in this inset. I am going to change. I am not changing any dimension of this page. So when I click here and click let us make it 4 mm. Now you see all these results. These are you see they are cut off. So that means our results are deleted from previous analysis. So whenever you are changing any design parameter from here, that will result in a deletion of your existing results. Okay, but that does not mean that that is completely deleted from a hard disk. It is still there, but right now it is not displaying here. When I double click here, then we see there are three tabs here. So in first, what kind of trace we were plotting. Then it is a primary sweep. That means on x-axis what we have, and in y-axis what we are displaying, that is we are selecting S11. Now if we go to families, so it will identify all kind of all the variables that have more than that have variations. So currently we have changed only L in. So this is displaying L in. Currently it was a nominal value. If we select all values and click apply trace, then this that cross marks has been removed. So here we see that L in equal to 7 graph is there. Now again for L in equal to 4 we have not analyzed. So again go to setup and click analyze. Uh, Everyone is able to see the screen, right?
Any queries?
Any queries till this point?
ठीक है सर, वही पूछ लूंगा मैं ये वाला चीज भी कि कैसा कैसा रहेगा फिर
Participants can write down their queries if you have any query.
और
Okay. Okay, so the simulation is completed. Now if I click here, you can see that there are two results, two traces of S11 for different variations. Okay, so now we have identified what are the variables, and we have designed our in our design we have made everything by variable. We are not hard coding any value, so we can change any dimension, and we can analyze their impact. And Let me see, check. Now, if there is one parameter that is LDEM, okay, that we have just set. Now, if I make it 0, uh, focus on this point if there are any changes. Okay, so now these results are present, although we have changed the LDEM, that is a variable, we have changed that variable, but these results are still present. These nominal values are still there. We have the nominal. Okay, these results are there, but I told you that whenever we are changing any variable, that variable will result in deletion of your current results. For example, if I change it again, fine. Now you see the this z parameter were displaying in nominal mode, so there is a cross mark here. So why this is happening? Because now let us go to this tab HFSS and select the design properties. In design properties, you see all the variables that we have created so far, they are of type design, whereas this variable is a post processing variable. So whatever change you make, it will not affect your design. So that is why was no variation there. Okay, so now let me reset this L into 4. Now our results are present. Now in the z parameter real part of z11, let me select this both the values and create a new report. So now in this new report, what we see here right now, I just told you that the resonance of the antenna is given by the peak value of the real part of impedance. But here we have not changed the dimension of this antenna, but still we are able to see that there is a huge variation. Earlier the peak was here, and right click here, go to marker, add a marker. So earlier the peak was at 2.1 gigahertz. Now the peak is around 2.2 gigahertz. Okay, and we are seeing that there are some extra peaks. That means it is a multi resonant antenna. So it is not like that, because as I told you that in the length of the if we travel around the length of the transmission line, the input impedance will vary, but the S parameter will remain same. Okay, you see, S parameter has not changed with that. Now the matching of has changed, but the S parameter is still there. Now if I click here and select 10, so what will happen? This is the z parameter, and I think this was the result we were investigating. So you see, when I change the post processing variable to 10, the variation in the resonant frequencies is shifted. If I click select this marker, right click here, go to marker, and ask it to search for the peak. Select this marker, right click here, ask it to go for the next peak. Okay. I selected M1, M2. M2, go here, go for the next pick. So both the you see there is a very small variation in the frequency in this case when I have changed this value LD embed to 10, whereas if I make it 0, the, the difference is very huge. Okay. So what is happening, that is why we use this in order to identify the clear the exact resonant frequency. What we need to do, we need to simulate the antenna at the point where it is connecting, at the point of the terminal antenna itself, at the terminal of the antenna. So this terminal antenna is starting from this. Okay, so and where we are adding our waveport, we are adding our waveport at this position. So in post processing, what we are doing, we are shifting this port, we are traveling along this transmission line, and we are reaching at this point. Because if you will go to the patch, and we had this feed line, if you select this feed line, you see in y size, the y size is extending starting from 0, and in y it has 10 mm length. So we have touched this wave port here when we are calculating the results. Okay, so that is when we are using the post processing, we have changed this here. So at this point we are now measuring the input impedance of the antenna. So that is why we are seeing only small variation. So same thing you can do when you are using the coaxial feeding. You can shift to this, uh, you can change this to 10 mm upside, so that it is touching the ground. If you are measuring at the ground position, you are measuring the impedance, then there will be very less uh, ma- div- variation in the peaks. Okay, so by this, now we can say that our antenna is resonating around somewhere here. Okay, why we are not exact? Because the position, the traveling we are doing, we are traveling along the line, but we are still, we have some gap between the ground and the micro strip that we have to account. So overall, we can have a decent antenna here, and we can identify the proper matching. So whenever you are identifying the resonance mode of your antenna, then you should be using de-embedding. If you are only considering the S parameter, uh, the S parameter will be less than minus 10 dB for a wide range of real and imaginary parts of the Z11. You can note down the range of real part of the Z11, that is 35 to 70, and 40 to 6, minus 22 plus 20, the imaginary part. Okay, so in this range, your S11 will be less than minus 10 dB. Okay, and we have also explored the field results also. Then this is your antenna, and now we have a good understanding of the different operations. Now let us see, we can have some field overlays here. So in HFSS, what you can do, you can select any surface, and you can see the field distribution at that surface. Okay, but for that you need to have saved the results. Okay, so let us click on, go here, select a face. Now I'm selecting the face of the substrate. Right click here, plot fields, go to E field, vector electric field. It will pop up a window in which you can select the solution type, whether it is the last adaptive solution or a sweep. So we are using a sweep, so we can use the sweep, and from that sweep we will be having all the frequencies that the simulation has been done. Okay, so let me select 3.38 gigahertz and click OK. So this is the electric field distribution, and this is displayed here. Okay, so this was the magnetic magnitude of electric field that I earlier created, and this is the magnet. Now right click here and go to animate, and you can animate it with different parameters. So let us create a variation. Click new. Now we have some variables. So first, most of the time, what we want to see the how the electric field is traveling inside. What is the effect along the time? So time, in terms of time, we see along the phase. So the input phase, as the input phase changes, how the electric field is being affected inside. So we are starting this phase from 0 degree to 350 degree in steps of 10 degrees. Now click OK and click animate. So you can see that these are the electric field lines that are varying. So from here you can see that these field lines are not rotating, they are slowly moving in one direction. Okay, so it also represents that our antenna is a linear polarized antenna. Okay, because you see these small variations are there, but there is a sudden change in this electric field, in the direction of this electric field. There is a sudden change. It is not slowly rotating in a circle. So you see that you don't have to focus on all the parameters. You see that fields that are dominating, like this is the index color coding, and if there is a electric field that has red tip, you select that, or according to this order. So I think we are able to notice this kind of yellow peaks here. So those peaks you can check their orientation. So they are either going up or down. These fields you observe, they are either going in the positive y direction or negative y direction. They are not rotating anywhere else. Okay, so we select the dominating electric field and we check their direction. Okay, that gives us the idea how the field is varying, and then if that was rotating around, then we should be going for the acceleration measurement. Otherwise, from here also we can identify that our antenna is linearly polarized. Okay. You can have you can change this plot, modify, go to modify plot and select the magnitude. So in magnitude we are able to see that around the patch we have this is maximum, this is 0, this is maximum, so it is a half cycle. Okay, uh, we can also plot the surface current, magnitude J surf, vector H fields, all kind of fields. We can see the electric field, we can see the magnetic field, we can see the vector current field. Okay, so this is the current field. You will see is starting from 0, maximum at the center of the patch, minimum here. So it is again a half cycle. Also apply the animation here, animate. So here you see the field is just going forward and backward, it is not rotating. Okay, so this is how you can design your antennas. Now if we can have another design in which we use aperture coupling, but that I am giving. There are four basic categories of feeding in microstrip antenna. One is direct feeding, that is coaxial feeding. Another one is microstrip feeding, and aperture coupling and proximity coupling. There are two more categories. So I am giving you some diagrams, some links to follow. You might find this in any standard antenna handbook, or or you can go for search. This is your inset feeding. This is a special feeding in which we are using the impedance transformer, and this is the coaxial feeding. This one is a different one. This is aperture feeding in which we have a ground plane that is cut by a slot, and we have a transmission line here. This transmission line and this slot, they are coupling this electric field is coupled to this patch antenna from this direction, from this slot. Okay, so I have designed this antenna here, but I want you to explore this design. So this is the antenna that I have designed. So I will give you these designs later on, but I want you to try to simulate these designs first. Okay, so similarly, one proximity coupling is there. You can find out about it in some books, or online resources are available. If you go to image search, then you will be able to find out these more. This is the pressure coupled feeding, and this one is proximity coupling. Okay, so on internet you can find various shapes. So there are a lot of shapes available. You can use your own designs. And for today, I am giving you a task to design an innovative, create an innovative antenna radiating at 3.5 gigahertz. And the design should be novel. Use your imagination or whatever. You can take some aspirations, and for example, if I click here in Microsoft, if I click on the design and select this, so this is also a unique design. This is also a unique design. If you want to create this kind of design, what you can do, you can select a cell and create a patch here, then create some uh, circles and cut them inside. So this kind of designs, uh, but if you can come up with your own design, then tomorrow we can go for a MIMO antenna with that design. If you are able to match that design properly, then okay. So I think some people have graph. Can you please explain radiation pattern graph and surface current density graph? Okay. So radiation pattern, for radiation pattern we had to create an antenna, sorry, a radiation sphere. So yesterday we have created a radiation sphere here. In radiation sphere, we select in radiation sphere is in spherical coordinate. There are three variables: radius, theta, and phi. So radius is fixed inside this. Then we vary theta from 0 to 180 and phi from 0 to 360 degree. So in 0, instead of 0 to 180 degree, what we are doing, we are varying both from minus 180 to plus 180 degree. And this is the step size. You have to select this step size carefully. If you select it like 2 degree, then at a single frequency you will require a lot of calculations. Okay, so based on your time in at initial points, when we want to display the antenna parameters like peak gain or XL ratio with respect to frequency, at each of the frequency point, it will go and check all the points. So that will be very time consuming. So what you should be trying, you should select this as a 10 degree for the initial phase. Then at the frequency range of interest, you select this to smaller values. Okay, then we have created this antenna. We, you can create a, one more uh, setup, infinite setup, that is for 2 degrees. Okay, so now we have two infinite spheres. Now let us go to the results and go to the plot. Let me delete all the reports. I have deleted all the reports. Now right click, go to the far field reports, 3D polar plot, and realize gain total. You function as a dB, and select the frequency and frequency sweep, and from here we will be selecting the frequency, but right now we are plotting at 2.5 gigahertz and create a new report. Okay, so here you see the it is displaying a 3D radiation pattern, and it appears to be correct, but if you check the value, it is the maximum gain of this antenna is minus 7 dB, right? That means minus 7 dB. That means instead of radiating the power, it is its amount is very less. Okay, so what we need, click on reports, results, right click here, create a model solution report, go to rectangular plot and create the S parameters. So now add a marker. This marker is here. It is 2.72 gigahertz. So again go to the your 3D, right click here, go here, 2.72 gigahertz. That was the design that we were working yesterday. Click here, apply. Now you see at 2.72 gigahertz, the maximum gain is 2.5 dB. That is your peak gain, and the direction of maximum gain is theta 050. Now if you want to calculate the field distribution, then you need to do, you need to right click on the field overlay here, or uh, you make all the things visible, or except the region. Okay, and click on the fit all. Now select a face on which you want to see the field distribution. So I want to select this face. Right click here, go to plot, select the electric field, magnetic field, uh, current density. So go to magnitude current density or vector current density, vector JSON, click OK, and at 2.5 gigahertz. So select here, go to here and select, double click here, right click, modify plot, and change the solution type to sweep. Now you are able to identify, select all the frequency ranges that we were discussing so earlier. So we are going to use 2.72 gigahertz. Click apply. Now it is taking some time. Okay. So if you go on the top view, you are able to see that this is the zero. The blue curves that are representing the magnitude, the field is minimum there. If there is a red one, that means that is the maximum, and uh, so it is zero going to peak, and then like it is like a sinusoidal wave, so it is a half wave variation. So Afrin, your first query was about radiation pattern and surface current. I think that is solved now. Mahesh, are the results from ANSYS are considered for research publication? Yes, you can publish a research paper with these simulation results, but nowadays the uh, only conferences accept simulation results, and most of the good journals they require fabrication results also. And I would suggest that whenever you are going for fabrication, uh, you must check your design and export that design and import that in CST. I will show you how you can do that in next lectures. So you try to simulate your design in HFSS and optimize that design. Optimization we will discuss tomorrow, how you can apply the parametric variation and all. But right now you do this from there. Then you have when once you have finalized the design, then go to CST, import your this design, you can export from HFSS in 3D, then import that design directly there and attach a wave port or whatever port you want, then simulate it. If both the results are consistent, then only go for design. Okay. uh, how can we check the mode from the current distribution graph? The mode basically represents TM01 or TM020, like this. So I need to identify the half waves variations of the field distribution. So if you see here, there is no this field distribution and this field distribution are almost identical. So there is no variation along this edge. Along y-axis, there is no variation in the current, but along the x-axis, there is half-wave variation. So by this, you can draw different fields and identify your variations. Okay, and can we add active component? Yes, you can add active components, but that requires some experience. And sometimes we make a copy. For example, we want to simulate the pin diode. Then pin diode has two stages, on and off. So what we can do, we can add those. Uh, we can develop two designs, and we can replace the pin diode by its impedance in on and off state. Okay. And in HFS with circuit simulation, we can use the other elements also. And it is possible to design yes, you can design IoT antenna in HFSS. You can design biometric wearable antennas in HFSS. Yeah. Any more queries?
Participants, if you have any query, you can ask. Sir has also given an assignment, a kind of a task.
Okay, so why TM mode only considered? Okay, so if you go through the theory of this TEM or TE or TM or TEM modes, then you will find that uh, if our boundary is surrounded by the metal, then we go for TE mode. If our boundaries are open, then we go for TM modes. Okay, you need to check out the uh, mo- uh, some book like Balanis, or you can go for the Sadi Q, and they have explained how you calculate the T or TM mode. Is it possible in spherical coordinate antenna? Right. Okay. I want to let us make it clear that do you want to create a spherical shape, or do you want to design your antenna in spherical coordinate? That that is a huge difference between if we want to implement on a spherical surface, or if we want to implement into whole structure into a 3D spherical coordinate, or you want to create some 3D objects. Okay, so spherical coordinates, that will be very difficult to analyze all the dimensions. For example, if you have a rectangular sheet only, how you are going to identify this spherical coordinate for that? Okay, so in order to model your design, in order to create your design, you need to have all the points, like which object is starting from at what position, and so all the 3D simulation softwares, they only allow you to model in rectangular coordinates only. They do not allow you to model in spherical coordinates. If you want to create spherical shapes, that is possible. If you want to create a sheet, then wrap that sheet around an uh, sphere or a cylinder, that is possible. We will also uh, check this that out in coming lectures. Okay, any more queries? So if there are no queries, then I have given you a task. You need to design an antenna. You need to change the optimize the variable dimensions. So what you need to do, you need to start with a please note down. You need to start with a simple patch antenna radiating at 3.5 gigahertz. So go to ChatGPT, ask it to calculate the physical dimension of the patch antenna radiating at 3.5 gigahertz. You give the substrate specifications like FR4, thickness is 1.5 to 4 mm. Then based on that dimensions, you create an antenna, optimize it. Okay. Then you change the shape of that. You add subtract some shapes from there, like this or like this. Okay. Or any creative ideas you might have. You might have seen any drawing. You might have seen any texture on your ground floors, so you can design that. Okay. Then it will give you a practice how you can go design multiple antenna elements, and how you that will give you a practice on the modeling part. Once you are efficient in modeling, then you can design any antenna, because the remaining steps are the analysis is simple. We have to make a proper setup. Okay. And then if you come up with a design that is properly radiating at 3.5 gigahertz, tomorrow I will show you how you can change that design to a MIMO antenna, and with that result only you will be able to uh, write down a good conference paper. Okay. If the antenna is giving high frequencies, but we want to bring it to lower frequencies using the same design. Okay, so if your initial design is for example, you have selected a random dimension, and you have simulated for a wide frequency range. You found out that it is radiating at 15 gigahertz. It is giving a resonance at 15 gigahertz, and you want to lower down the frequency to 5 gigahertz or 2 gigahertz. What you need to do, you need to increase the size of that. uh, for example, from 15 to 5 gigahertz, that is a difference in 3 times. So you need to increase the length of the patch by 3 times at least. Then in order to match the impedance, you need to change the width also. Okay, so do not start by any random dimension. Now we have many AI tools that we don't have to use the formulas, and you can just go to ChatGPT or Gemini or any other tool, give them the dimension that I am designing an antenna at this frequency. These are my substrate. Then they will give you the dimensions. Okay, so start with that dimension. Otherwise, what you can do, you can go through the some books like Balanis, and you can use the formula in Balanis antenna design and analysis by Balanis. There is chapter 14 that is dedicated for microstrip antenna, and they have some given some examples to calculate the dimension. So you can follow that. Okay, Mr. Abhishek, we will be discussing this wrapping of a sheet around any object tomorrow.
Sir, I think now there are no more questions.
Okay. Okay, I hope so. This session was made insightful for you, and I'm hopeful that the most of the participant will complete the given task.
Yes.
Okay, so thank you everyone.
ठीक है।
Thank you, sir. Thank you very much. The session was very much useful, sir.
Okay,
And dear participants, tomorrow's session will start from 9 a.m. So you are requested to kindly join by 8:45 to avoid any delay.
okay, Swati.
Thank you,
Uh,
sir.
okay, thank you for inviting me.